When we talk about multi-agent systems in artificial intelligence, we are talking about environments where multiple decision-making entities, which we call agents, exist at the same time and influence one another. Unlike a single-agent system, where one agent interacts with a passive environment, a multi-agent system involves agents whose environment includes other agents. Those other agents may cooperate, compete, negotiate, communicate, coordinate, deceive, or learn from each other. This simple shift from one agent to many changes the conceptual and mathematical foundations of the system in profound ways. Let us begin by clarifying what we mean by an agent. In the most abstract sense, an agent is an entity that perceives its environment through observations and acts upon that environment through actions in order to maximize some objective. In reinforcement learning language, we describe this in terms of states, actions, rewards, and policies. A policy maps states or observations to actions. In a single-agent Markov decision process, the environment dynamics depend only on the current state and the action of that single agent. The reward function also depends on the state and action. The agent tries to learn a policy that maximizes expected cumulative reward over time. In a multi-agent system, the dynamics depend on the joint actions of all agents. If there are n agents, each with its own action space, the next state of the environment depends on the combination of all n actions. Likewise, the reward received by each agent may depend not only on its own action, but on the actions chosen by others. This introduces strategic interdependence. The best action for one agent depends on what it expects other agents to do. That expectation, in turn, may depend on what those agents believe about this agent. We quickly enter the territory of recursive reasoning in game theory. To formalize this, we often use the concept of a stochastic game, sometimes called a Markov game. A stochastic game generalizes a Markov decision process to multiple agents. There is a set of states, a set of actions for each agent, a transition function that maps the current state and joint action to a distribution over next states, and a reward function for each agent. Each agent aims to maximize its own expected cumulative reward. When agents have conflicting objectives, the situation becomes competitive. When their rewards are aligned, it becomes cooperative. When there is partial alignment, we get mixed motive scenarios. At the core of many multi-agent systems lies game theory. In the simplest static case, we can consider a normal form game. Each agent chooses an action simultaneously, and the payoff to each agent depends on the joint action profile. A central concept here is the Nash equilibrium. Informally, a Nash equilibrium is a set of strategies, one for each agent, such that no agent can unilaterally improve its payoff by deviating from its current strategy, assuming others keep theirs fixed. The mathematical condition for a mixed strategy Nash equilibrium can be summarized conceptually by the condition that each strategy is a best response to the others. This expression encodes the idea that, at equilibrium, the utility of agent I under its equilibrium strategy and the other's equilibrium strategies is at least as high as under any alternative strategy it might choose while others remain fixed. In multi-agent learning, we often aim to design algorithms that converge to such equilibria, although convergence is not always guaranteed. In dynamic environments, agents interact over time. Their actions today affect future states and future rewards. This brings us back to reinforcement learning, but now in a multi-agent context. Each agent may learn through trial and error, updating its policy based on observed rewards and transitions. However, the environment is no longer stationary from the perspective of any single learning agent, because other agents are also learning and changing their policies. This non-stationarity breaks many assumptions of classical reinforcement learning, where the transition dynamics are fixed. Consider independent Q learning in a multi-agent environment. Each agent treats other agents as part of the environment and applies standard Q learning updates. In a single-agent stationary environment, this update converges under certain conditions. In a multi-agent setting, however, the transition from S to S depends on the joint action, and other agents' policies may change over time. Therefore, the target value or plus discounted max Q at the next state is not drawn from a stationary distribution. Convergence guarantees often fail. Despite this, independent learning sometimes works in practice, especially in cooperative settings with aligned rewards. In cooperative multi-agent systems, agents share a common objective or receive identical rewards. The system can be viewed as a single distributed agent, but with decentralized control and possibly partial observations. A central challenge here is coordination. Agents must learn to act in ways that complement each other's behavior. For example, in a team of robots moving an object, each robot must coordinate its force and direction with the others. In communication networks, nodes must coordinate transmission schedules to avoid collisions. One approach to cooperative multi-agent learning is centralized training with decentralized execution. During training, a centralized critic has access to the observations and actions of all agents. It can evaluate joint action values and provide more informative learning signals. During execution, each agent acts based only on its local observations. This approach leverages extra information during training to stabilize learning, while preserving decentralized policies for deployment. Architectures such as multi-agent actor-critic frameworks implement this idea. Credit assignment is a major issue in cooperative systems. When the team receives a shared reward, how does each agent know whether its action contributed positively or negatively? If the reward is sparse or delayed, learning can be extremely slow. Techniques such as difference rewards attempt to estimate the marginal contribution of each agent by comparing the global reward with and without that agent's action. Value decomposition methods attempt to factor the global value function into components associated with individual agents, enabling more structured learning. In competitive multi-agent systems, agents have opposing objectives. Classic examples include board games like chess or Go, zero-sum games where one agent's gain is another's loss. In such settings, learning can be framed as finding a minimax solution. In a zero-sum two-player game, the value of the game under optimal play can be expressed as the maximum over one player's strategies of the minimum over the other player's strategies of the expected payoff. This min-max structure defines equilibrium in strictly competitive environments. Self-play has emerged as a powerful method for training agents in competitive environments. An agent trains by playing against copies of itself or previous versions of itself. Over time, this can produce increasingly strong strategies, as the agent continually adapts to stronger opponents. However, self-play can also lead to cycling behavior, forgetting of earlier strategies, or exploitation of weaknesses in specific opponents rather than robust general play. Techniques such as maintaining a population of policies and using league training help mitigate these issues. Between pure cooperation and pure competition lies a vast space of mixed motive interactions. Consider economic markets, traffic systems, online auctions, or resource allocation problems. Agents may compete for limited resources but also benefit from maintaining stable systems. Mechanism design becomes relevant here. Instead of simply analyzing equilibria, we design the rules of interaction so that self-interested behavior leads to socially desirable outcomes. Auctions are a classical example. By carefully designing the bidding rules, we can incentivize truthful reporting or efficient allocation.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.